Okay, I'd like to close the section on introduction to material property differences by talking about some of the color aspects of ceramics. We already mentioned that it's important that ceramics can be transparent or translucent. Important in dentistry to replicate the appearance of natural teeth. Of course, important in other applications where we want to see through windows, see through our drinking glass, applications like that. You've already learned about contrast ratio, that a contrast ratio that is low, a contrast ratio that is close to 0, would be for a perfectly transparent material, and a contrast ratio that is close to 1 would be for a perfectly opaque material. So a translucent material would have a contrast ratio somewhere between 0 and 1. And whether or not a ceramic is translucent comes back again to the largely to the porosity in the material. If there's a pore inside the material, then light rays striking the pore will be scattered in many different directions, providing diffuse reflection and making the material not transmit light directly. We can see an example here is the alumina or aluminum oxide that is used to make very bright light bulbs. These light bulbs are encasing sodium arc lamps. These are used for the really bright street lights on top of highways. You might have noticed that street lamps on less traveled streets tend to overheat and turn themselves off until they cool down, and then they turn back on again. Those street lamps have glass casings, and they can't be allowed to get too hot or they will deteriorate the glass casing. However, for applications where we need a really bright hot light in the middle of the bulb, and we can't have that bulb turning off periodically like over busy highways, then we have to use a sapphire material. The light bulb is actually made out of sapphire, and alumina or aluminum oxide is the chemical name for sapphire when it's crystalline. And so we see all these microscopic crystals. In the case of pure aluminum oxide, it's difficult to process without having a lot of pores in the middle of the crystal grains and at the boundaries between the crystal grains. And these pores scatter light, and you can see that if you take a bar of the material and lay it on top of writing, you can't read the writing through it. It's completely opaque. However, if we add 0.5% of magnesium oxide to the aluminum oxide and process it carefully, we can remove all of the porosity and also get smaller crystal grains. And that leads to the material being so translucent, it's almost transparent, and we can read the word translucent through a bar of the material. So this is a special type of transparent sapphire called Lucolox, patented a long time ago by General Electric Corporation. And incidentally, it was discovered by mistake, by accidentally having magnesium oxide impurities in a batch of their raw material. But fortunately, they learned how to replicate the mistake reliably. Also notice that I mentioned the size of the crystal grains in this material is smaller than the crystal grains in the opaque material. That has a small effect on translucency or transparency. If a crystal grain is small enough, then it tends not to interact with visible light waves, and so it makes the material more translucent or transparent if the crystal grains are smaller. And this is becoming important in some zirconia materials because zirconium oxide has a very high optical index of refraction, higher than that of diamond even. And so the light refracting at the grain boundaries in the material makes this very opaque and bright white material that is not suitable for aesthetically replacing teeth. We'd like to use it because it's one of our stronger ceramics. And there's research being done now. In fact, it's already been patented, but it's not currently on the market yet, to make zirconia with very tiny grain structure that is supposed to be translucent instead of opaque. So we'll see where that leads. Another example of light scattering involving ceramics is if you put a ceramic material inside a polymer matrix, and it has a similar effect to putting pores inside of a ceramic matrix. This example comes to us from orthodontic brackets. We see here a dental bracket made from polycarbonate plastic. Looks transparent. And then if we introduce microscopic glass fibers to scatter the light, and this is polycarbonate matrix in between the glass fibers, then we get a bracket which looks more tooth colored. It's not transparent, it's translucent, because it's glass fiber reinforced. And there's a difference in the optical index of refraction between the glass fiber and the polycarbonate material. An example of where porosity would come in is with orthodontic brackets made entirely from ceramic. This is one made from a single crystal of sapphire, aluminum oxide. And this is also made from aluminum oxide, but it's made from a bunch of small crystals that have pores in them and between them, and leads to the material being translucent in this case. Because it has pores to scatter the light. And the single crystal has no pores, or very few trapped in it. And it has no grain boundaries because it's only one crystal. No boundaries between crystals. And so that's why it's transparent. And then we look at, in addition to the transparency, we can change the hue in ceramics through a broad spectrum very easily. Usually this is done by adding metal oxides where the metal is lying in the middle of the periodic table of the elements. So we have a short section in the middle of the periodic table of the elements called the transition metals. Oxides of those metals are very potent additives in changing the hue of ceramic materials. Minute addition of transition metal oxides causes can cause very bright changes in color with more. And it's not just which transition metal oxide you choose that controls the color. It can also be how much of it that you add that controls what type of color you're adding. For example, iron can be +2 charge or +3 charge in a glass material depending on how much of it you add. And if you add a little bit, you will get a green colored glass, and then if you add more and more iron, still not too much, but if you add more iron oxide, then the glass will turn brown. Okay, so that concludes the portion where we will compare differences in material properties with other classes of materials. The next topics that we will go over will be methods to accommodate the low strength and low predictability of strength in ceramics, and methods used to process ceramics in spite of their very high melting points. For now, I want to leave you with pages in your textbook. The textbook describes things in a little bit different way than I did, so it may be useful for you to read it in addition to listening to these lectures. And I've included 2 sets of pages for each topic. The first page range is for the old version of the book, the 11th edition. You should have in your Vital Source textbooks now the 12th edition, and that will be the new page range numbers.